Okay, it's a pleasure and honor to be here to take part in these celebrations. So let me begin by saying happy birthday, Spenta. I have known Spenta for many years. The first time I met him, I was in kindergarten. And, and I remember that was the first time, actually around the first time, when I saw the Nambugoto action written on the blackboard. And then Spenta in his Italian Parsi accent said, "This is very important." And I understood that string theory was something exciting. And then I went to do a summer project in TIFR. And what struck me there was that it was evident to me, even as an undergrad, that Spenta had really brought some new vitality to the group. And people like, there were Avinash and Sanjay and Shanks, they were all students, and they were excited about really the frontline things that were happening elsewhere. And somehow in the 70s, somehow India was a bit left behind in the quantum field theory revolution. And I think now, of course, the Indian scientific community and the string community is really one of the major forces in string theory internationally, and we sort of take it for granted. But in those days, string theory, India was really on the periphery of research. And of course, we have been fortunate. There was a steady stream of outstanding string theorists coming from India, but Spenta played a very pivotal role in bringing India to the center. I should also say that then I was his colleague in Tata Institute, and then I've known him in other capacities. For example, as a chauffeur in his famous Fiat, because his children and my daughter were same age, and we used to share responsibilities to drop off the children, and they were very good friends of my daughter. And then later on, I got to see also his organizational acumen. We organized Strings Conference in India for the first time. Once again, when it is the first time, now it looks obvious, but to have a major conference like that in a developing country was a big deal, sort of a big step. And it was good to see Spenta, one of his can-do attitudes was certainly responsible for this. And I remember Sunil was also one of the organizers, and one evening, sort of finishing off a bottle of Lagavulin, trying to figure out all the details of this conference. And I don't know if the Lagavulin helped the organization, but I know that I discovered that strong liquor has a good effect on people with strong opinions. So, finally, I should say that, okay, I have also had the Spenta's wonderful wife, Lena. I have enjoyed their hospitality in many places around the world. And now Spenta's this next move in ICTS. I should perhaps say that he mentioned Jawaharlal Nehru. So Jawaharlal Nehru said that the scientific institutions are the temples of modern India. And it is, I think Jawaharlal Nehru appreciated that. Of course, in a country like India, the demands on resources are very complicated, but he realized that science, to build a nation from the colonial ruins and the weight of the past, science is going to play an important role, and he really wholeheartedly supported the Tata Institute, and ICTS really continues in that tradition, and I wish ICTS all the best. So let me now move on to my talk. So once again, happy birthday, Spenta. So I'll talk about some recent work I've been doing on Weyl anomalies and their possible role in cosmology. This is work done in collaboration with my student in Paris, who's actually now going to be a exchange student here for 6 months. Then André Benavides, who is a student in ICTP, Akash Goel, who is at Princeton, a graduate student, and Alba Grassi, who is a postdoc in ICTP, who will be going to Simon Center next year. So the basic, let me say the motivation for this work The main question that we would like to address is that there can be an anomalous dependence on the scale factor of the metric. So this is a completely anomaly. I have worked most of my time in the ultraviolet side of quantum gravity. This is really the infrared side of quantum gravity. Very long wavelengths. So logarithmic scaling violation due to renormalization, viewed as Weyl anomalies, they lead to an anomalous dependence on the scale factor of the metric. And since the scale factor undergoes several e-foldings as the universe expands, large logarithms are involved. So even if these quantum corrections are small, they can add up, they can pile up. And so the question I wanted to sort of address was, can we compute these effects systematically? And can they lead to interesting effects in cosmology? And the main tool is going to be that the leading large logarithms can be resummed using local renormalization group to obtain a non-local quantum effective action. And I will now give you a couple of examples where it has interesting effects. So to start with, instead of plunging into 4 dimensions directly, I'm going to consider, I first analyze a simpler model in 2 dimensions, which has all the essential features, but the computations are much simpler. So basically, you start with Einstein gravity in d dimensions and take a limit d equal to 2 plus epsilon. And one can show that the action reduces to basically time like Liouville theory. So you recognize this as a Liouville theory, but with a wrong sign kinetic term. And the cosmological constant, square root of g, because the metric g mu nu is e to the 2 omega h mu nu, then in 2 dimensions, plus order epsilon corrections. So it looks like exponential operator e to the 2 omega. Alternatively, one can obtain this action as a Polyakov action for supercritical matter. And classically, when the cosmological constant is positive, it admits de Sitter as a solution. Now, it is well known that the cosmological constant operator e to the 2 omega, even in free field theory, you know that, has anomalous dimension 2 beta square. It's a bit like tachyon vertex operator, which has anomalous dimension k squared, which is ik dot x. So with the normalization I have chosen, the anomalous dimension of this e to the 2 omega is 2 beta square. And therefore, it implies that the trace of the energy momentum tensor must receive a quantum correction. So if you take a cosmological constant term in d dimensions, then it is just lambda g mu nu. If you take the trace, it becomes minus 2 times minus 2 or minus d. So this is the classical piece, but in order to accommodate for this anomalous dimension, it should have a quantum anomaly. Another way to think about it is that in order to renormalize the operator, you have to renormalize the operator in some background metric, and that introduces an additional dependence on the background metric, which was not present classically. So the quantum renormalized operator has an additional dependence on the background metric, which is what is responsible for these anomalies. Now, you can ask, given this trace in 2 dimensions, in fact, given 2 conservation equations and a trace, there is a unique covariantly conserved quantum momentum tensor, because you have 3 equations for 3 unknowns, but it must be non-local, simply because anomalies are precisely those effects which cannot be removed by local counter terms. We expect it to be a non-local object, and here it is. It's a okay, so you can calculate this in many different ways using heat kernel methods in curved space-time, just by using conservation equations. So it looks pretty scary. And you can check that del mu T mu nu is 0, and trace T mu nu is what I gave you before. And in beta going to 0 limit, it reduces to the classical energy momentum tensor. And you can show that it follows from a non-local quantum effective action. If you write the metric, this is the conformal factor of the metric. In 2 dimensions, G is conformally equivalent to a flat metric. And it has it can be expressed as a non-local functional of the metric, where by just inverting this relation, so it's like a Laplacian acting on omega, the curvature, if the background metric has 0 curvature. So just inverting this equation gives you this green function times r. So it's manifestly non-local action. Yeah, it is that. Green function is 1 upon del square r, right? No, so the point is that it is appearing with the cosmological constant as well. There is, so that's.
Set the cosmological constant 0 then.
No. So there is an addition and contribution coming from the usual Polyakov anomaly. This is not what I'm talking about. I'm talking about the renormalization of the cosmological constant operator added to the Polyakov action. But this also is known in the Weyl literature, and this is what is behind the KPZ critical exponent. So it's a very well understood subject, both in space-like and time-like. Now, we want to understand the cosmological consequences of this. If you consider a homogeneous and isotropic universe, you can write the metric in this way. Then the stress tensor has to be of this form, and the trace of the stress tensor now is no longer 0. So once again, by using conservation equations, you find that pressure is not proportional to rho with the coefficient -1, which is what you normally expect for cosmological constant, but there is a small correction plus 2 beta square. Yeah. So that R1 upon del by R is actually the analog of this R upon epsilon term here. The new thing that is present when you have a cosmological constant. And that you added by hand? Yeah, that because we want to study in Weyl theory also, you add it by hand because you want to study a theory with a cosmological constant. So the motivation is to take, that's what you would get for just a free field, but the Weyl theory has, so if you want a d-dimensional quantum gravity with cosmological constant, it reduces. To start with, then you had another conformity theory. Yes. That out. Yes. Yeah, the way I motivate it is that you don't need a conformal field theory, but you could do it that way, as I said. You can imagine it as a Polyakov action, but these two things are equivalent. But that difference is not important for our purpose. So the main point is that because the cosmological constant operator has anomalous dimension, the trace is modified. Because the trace is modified, the stress tensor itself is modified, but the modification has to be non-local because it captures the anomaly. And if you now put it onto homogeneous isotropic universe, then it modifies the barotropic index of the cosmological fluid slightly from -1 to -1 plus 2 beta square. So the non-local momentum tensor, first of all, it becomes effectively local because of the symmetry of the problem. So this horrible looking non-local expression actually simplifies greatly. And you get this very simple relation, which you can now solve these Einstein equations. And the net effect is just to modify this barotropic index. And what you find is rather interesting. What you find was that, as I told you, classically, the time-like Weyl theory or this gravity in 2 plus epsilon dimension had de Sitter as a solution. But once you include these quantum corrections which are proportional to beta square, the de Sitter expansion gets modified to a power law expansion. So you get quasi-de Sitter power law expansion. And a dilution of vacuum energy. The vacuum energy is no longer constant because the barotropic index is different. And rho changes as in this manner. And you can see that this can be expanded out in terms of infinite number of logarithms. So what we have done is effectively we have resummed the leading logs, which is what we will use local renormalization group to do. So basically this is an effective, in Weyl theory we didn't need to do anything like that. In 2 dimensions we could just do it directly, but in 4 dimensions we'll use local renormalization group to do this. The main idea is that because large logarithms are involved in cosmology, they could lead to interesting effects, and here is an example where they do, that by integrating this, you slow down the de Sitter expansion and it leads to a dilution of vacuum energy. And for this, large logarithms have to be resummed. And note that there is no particle production. You might ask, what happened to the vacuum energy? It doesn't disappear into some producing particles. So this is quite different from mechanisms, say, imagined by people like Polyakov and Mottola. What happens is that it's a kind of a non-linear dilution of vacuum energy. The vacuum polarization modifies the equations of motion of the cosmological term, and then it back reacts onto the geometry in such a way that it's a kind of an interesting 2-dimensional model which sort of captures this. It's an example where, just to convince yourself that the Weyl anomalies can play an interesting role. So, beta going to 0 is the center charge of the extra matter going. So so beta is equal to 1 upon q in this, and central charge is 1 minus 6q square of this Weyl theory. And then you have to add matter to cancel anomaly. Central charge of this theory goes to minus infinity. So it's a supercritical matter. Yeah, because it's time-like level. You are putting supercritical matter if you want to think in that language. But I want to think in this language because it's kind of closer to the four-dimensional thing. It's a limit of the four-dimensional theory. I don't need to think about it. Yeah, you do because you are in 2 plus epsilon dimension. So 2 plus epsilon dimension is actually equivalent to having a Polyakov action. Okay, and you will see that actually we'll do these same calculations in a differently, which in a manner that is valid in all dimensions. And when we take the 2 plus epsilon dimension limit of the kind we did, we'll recover the Liouville result. So that's therefore I want to think about it in that manner. Yes. Yeah, except when beta goes to 0. When beta is non-zero, so you might ask what we have done. And basically what you're choosing is, what you're computing is a T mu nu in some in state. It's like a Schwinger-Keldysh formalism. And the in vacuum you have chosen is the conformal vacuum. So the metric is flat. And you choose the vacuum, the Bunch-Davies vacuum that normally one chooses is actually the conformal vacuum. And when you have massless particles present, the Bunch-Davies vacuum doesn't have the full de Sitter symmetry. So it's not. Yeah, there exists a solution. You could, but that is actually somewhat unnatural. It's a bit like, okay, I will come to that in the end probably because I won't finish otherwise. There could be more solutions, but I have assumed a homogeneous isotrope. Yeah, generically in Liouville theory there could be, but after imposing Virasoro constraints, then there will be one solution.
And this is that one.
Yeah, this is that one solution. Yeah, in this theory there is only one solution. No, but his question is he's worried about de Sitter invariance, and it's a good question, but I'll come to that. Okay, generalizing to, so we expect a similar modification. So I told you this can be summarized by this effective action. This complicated stress tensor follows from this effective action. And you would expect something similar in 4 dimensions. And in general, however, the anomalous dimensions in higher dimensions will depend on the scale, because in 2 dimensions, the gravitational coupling constant was dimensionless. And because of that, basically the anomalous dimension was constant. It's 2 beta squared. But it would be a function of, generally there will be a non-trivial beta function. Moreover, there will be all standard model fields with non-trivial beta functions. So one would expect a Weyl anomalies and anomalous Weyl dependence on the scale factor more generally. So the question I want to ask is now, given the fact that we have standard model fields and they have beta functions, can we really study this anomalous dependence on the scale factor in cosmology in some systematic way? So I want to sort of broaden my question, not just gravity, but I gave you an example where it was pure gravity. But now consider a generic quantum field theory and ask the question in curved background. So can we compute the quantum effective action at one loop depending on classical background metric, which is the cosmological Robertson-Walker metric? And in principle, this is a completely Weyl-Post problem. You have to do, of course, ghosts and so on, gauge fixing. But the effective action at one loop is simply given in terms of trace of some heat kernel in this curved background. It's a Weyl-Post problem, but it's basically forbiddingly difficult, intractable in general, basically because you have to solve to find the heat kernel, the Schrodinger problem for an arbitrary potential, which you cannot do. So you have to resort to some approximations, and moreover, it's not enough to use the usual Schwinger-Dewitt expansion, because, which is valid for short proper time, because we have to integrate from 0 to infinity, and we really need the heat kernel for all values of the proper time. So what do we do? Well, fortunately, Barvinsky and Vilkovisky have over a period of 10 years, they wrote a number of very nice papers which were not many people know about. And they developed a curvature expansion completely covariant in this limit that the box R is much bigger than R squared. And it's not a derivative expansion. And and they have an completely explicit formulas. But just to give you an idea, we are not going to use this because it looks like this. The trace is some integral over, this trace is just a trace over species. It's a small trace. And this script R are various curvature tensors. They are evaluated at different points at space-time. And these form factors, Fij, are complicated non-local form factors which depend on the Laplacian. And this typical function, form factor comes from a function like that. So if you put, you can imagine here, if you put x to be a box, it's a very complicated function of the box. And there are, to the order that we're interested in fact, there are some 30 terms with very precise coefficients, which you can read up from their paper. And you might think, how can you even trust this calculation, apart from the fact that these are strong Russian quantum field theorists. But they have actually, you can actually get, this complicated expressions give better insight into anomalies. For example, in 4 dimensions, one can derive the Riegert action, which is the analog of Polyakov action, including there are some extra terms which are independent of the scale factor. There was a lot of debate in the literature between, say, Deser and various people had written papers. So this really resolves and gives you a very clean answer to that question. Unfortunately, the regime in which they are working is not the regime of interest in cosmology, because in cosmology everything is of Hubble scale. So this looks like, even though it's a useful expression, is not going to be the one that we want. And so what do we do? Well, what we do is we use local renormalization group, which was developed by Osborn as a way of proving the A theorem and the 4-dimensional A theorem. And the main idea is that if you're working near some UV critical fixed point, I mean, let's say Gaussian fixed point, and you have some perturbations, you want to study, there is the renormalized theory along the RG flow. And I mean, intuitively one can understand it easily that there is no reason why physicists in Andromeda galaxy should use the same RG scale as us. So RG scale is expected to depend on position, and therefore you can expect, instead of the integrated equation, so the normal RG Callan-Semanzik equation is really the integrated version of that, but you expect an analogous local version of it, which says that trace of the stress tensor is given in terms of beta functions times the operators renormalized in that metric. And that's where the non-local dependence comes in. Now the advantage of this approach is that the beta functions are determined by the non-local short term, because they are just short distance divergences in the UV short distance divergences. So you can just use the local Schwinger-Dewitt expansion and you don't need to resort to Barvinsky-Vilkovisky. And moreover, in the Robertson-Walker background, the entire classical dynamics is contained in the scale factor. You can regard this as a functional differential equation for the factor omega and integrate this to obtain the answer. So basically, the idea that we use is to deduce the non-local action from Weyl anomalies. The local RG equation gives the functional derivative for the action in terms of the beta function as an anomaly from the fixed point, and functionally integrating this equation completely determines. However, there is non-trivial dependence on which depends on the logarithm of the Laplacian. These are the terms independent of scale factor, and which took us a lot of time to figure out how to do it correctly. But they can be determined, we realize in the end that you can determine from the flat space limit. So putting it all together, you can basically completely determine the action for cosmological spacetimes, which is what our interest is. So notice here that even though the background metric is fixed, we have integrated our graviton loops. So we are doing some kind of a background field calculation. So even though the background metric is fixed to be the Robertson-Walker form, we are not assuming that the graviton loops have any restriction. So just to give you a general, a simple example, just consider massless charge fermions integrated out, QED. And this is the answer we get. It's much simpler than what Barvinsky-Vilkovisky would give you. And it's intuitively very easy to understand. This factor is basically the anomaly. So it gives you the anomalous depends on omega. Omega, you remember, is the log of the scale factor, plus a piece that would reproduce the beta function in flat space. This is the complete answer that we deduce just from this simple local RG. And the advantage of the Barvinsky-Vilkovisky is this is what you would get from Barvinsky-Vilkovisky. So the advantage of the Barvinsky-Vilkovisky is, of course, is that you have something to check your answers against, because you trust these people, perhaps more than yourself. And you can see that actually all these terms very beautifully cancel out. Yeah. I'm taking it to be just Robertson-Walker form. Yeah, tau. Yeah. No, in general it will, I mean, this answer is for omega depending generally on x, and then we can specialize it when into Robertson model. Okay, I have 5 minutes, right? So all but the first two terms vanish, and our result agrees with Barvinsky-Vilkovisky. However, it has now much larger domain of validity because it does not use this approximation which they used. We have done it using the local string derivative expansion, and we can use it to now really study effects in cosmology. While flatness is, we have assumed.
No, but they don't.
No, that's right. But for cosmological, but for cosmological spacetime that I'm interested in, it's more important for me to be able to calculate it without assuming low curvatures. But their results are certainly more general than ours. Yeah. No, so I'm imagining in the early universe, for example, when the Hubble scale is much bigger than the, much heavier, very early universe, all the fermions were massless, so the Higgs field was up. No, not in temperature, before inflation, for example. It doesn't have to be finite temperature, right? Before inflation, when the universe was expanding, during the inflationary phase. Yeah. The Higgs has not condensed. Okay, so our result, so this is what I'm coming to, in fact, that an application, primordial magnetogenesis, this is just to give you an example where this can be applicable. So there are observations of TeV scale photons, and the TeV scale photons are actually expected to also give rise to GeV scale photons by upscattering the CMB radiation. And people have observed the TeV scale photons but not observed enough GeV scale photons. And from this, people have put a lower bound on the intergalactic magnetic field of this kind, 10 to the minus 15 Gauss, over the scale of megaparsecs, which is extragalactic. And such large scale magnetic fields cannot be generated by local processes in the galaxy, and they have to be primordial in origin. Of course, this bound is there is debated, but it's kind of to be taken with a, everything is not settled here, but it is taken sufficiently seriously that it's an effect that is possible, but it's from a non-observation, there is no direct observation yet. But therefore, it's an interesting question, can we generate this primordially? And if you try to generate an inflation, then it's evident that the classical Maxwell field simply does not notice the inflating universe. So the classical Maxwell field can never generate such things. Whereas now, if you have a Weyl anomaly, it has this anomalous depends on scale factor, and there is a possibility that the quantum fluctuations of the Maxwell field can get amplified during inflation, much like for a scalar field. And you can work things out, and they depend. Yeah, so cosmologists sometimes just put an arbitrary coefficient, but this is completely universal in that it's determined just by the your charge content of the theory, and you don't have to assume some scalar field giving a time dependent. So it's an interesting question, and one can put bounds on it, which is determined in terms of the Hubble scale factor, and this is some work in progress with a cosmologist. So just to show you that the result that we got by this long calculation, following the analogy with 2 dimensions, already you can see interesting applications in cosmology. In pure gravity, we have been able to, we deduce that the gamma lambda that we had at one loop, we find this is 0. I mean, you can go to some particular field redefinition, and you can, gamma lambda is determined to be this, and we find a quasi de Sitter solution much like in 2 dimensions. Of course, here the effect is much small, is suppressed, Planck suppressed, because Planck constant is dimensionful in 4 dimensions, but it can be appreciable in the early universe. And there could be an interesting analog in the ADS context, but the boundary conditions have to be, which would say that the ADS, which would be interesting for the quantum stability of anti-de Sitter spacetime, but the boundary conditions have to be analyzed carefully, and this is something that we are thinking about. So in summary, I showed you a 2-dimensional model which exhibits an interesting mechanism for dilution of vacuum energy that slows down de Sitter expansion to a power law expansion. In 4 dimensions, the non-local modification due to these Weyl anomalies can be computed using the local RG for Robertson matrix. And we have done it for all the standard model fields. And there are all kinds of issues about gauge invariance and so on, but I think we pretty much understand those. And these non-local quantum effects can have interesting implications for cosmology, for example, primordial magnetogenesis and stability. I mean, in the very least, one can put some bounds on the scale of inflation and things like that. and the stability of anti-de Sitter spacetime. So with that, I will end my talk, and let me end my slide. I started with this quote of Pandit Nehru. So here we are in a temple of modern India, and I wish all the best to the ICTS team. I think with Rajesh as the director of ICTS and Sandeep as the director of TIFR, I think the future is in able hands, and I am sure that they will steer this institute in the right direction. Sandeep had some important, being the director, he had some important duties. He told me. Okay, thank you. Huh? Yes.
Questions?
Yes,
Questions for Atish?
Yeah.
Is it amount to use
infrared quantum gravity effects? But not just quantum gravity, as I showed you. Integrating our charged particles is just, those are just fine structure, suppressed by fine structure constant.
Oh.
So, I mean, in general, if you have particles which are massless compared to the Hubble scale, then you expect non-local effects of this kind. And it's since cosmologists are now getting high precision experiments, it's interesting to ask whether such non-local effects during inflation could have appreciable effect. Yes, I think it would work the same way for non-abelian. And when it becomes strong, I think it's an interesting question of how to treat them. Yeah, they could have, but I think if QCD phase transition happens after inflation, then they would not affect, presumably, they will not leave any signature on inflationary. For example, you might expect some color magnetic, primordial color magnetic field. But those, yeah, so it's an interesting question actually to analyze possible effects of this for PCD.
So to have infrared effects at large scales, right, you need really massless particles, interacting massless particles, yes. Right? So I understand that if you have massless charge fermion, then they could produce infrared effects, but in pure gravity,
graviton is the
so graviton, but the graviton interaction is
yeah, so
falling off in the infrared, right? I mean, it's
suppressed by h square upon m Planck square. But if you have pure gravity,
yeah,
like in today's universe, it will be highly suppressed.
But when h is of order m Planck, then that's not really an infrared effect, right? That's more.
If h is suppose of order h square upon m Planck square. So by the way, so the gravitational wave limits already put h square upon m Planck square to be 10 to the minus 10. So in the inflationary window, unfortunately, these effects are not important in 4 dimensions. But they could be important early in the, earlier when h is say 10 to the 17 GeV and m Planck is, so at that time you will see kind of quasi-de Sitter expansion because of these effects. Secondly, I think it's a question of principle, whether de Sitter is really the stable state or final state is a quasi-de Sitter state. In principle, graviton will always remain massless. So this quasi-de Sitter thing will slow down more and more and more, but eventually.
So I think even in 4 dimension, the effect of this will be to destabilize de Sitter. Is that right?
That seems to be our conclusion. So, yes. And maybe if I have a minute, I can come back to your question, because you might ask, how come you broke de Sitter invariance, right? So the point is that it's a question of choice of the initial state, which is always a very subtle question. But I mean, to take you an example, I think this is something that Sasha Polyakov has emphasized. That if you have, suppose you prepare a black hole state in the Hartle-Hawking state, then you will never see Hawking radiation. So but the point is that the Hartle-Hawking state is an extremely fine-tuned state in which you're sending in precisely Hawking radiation as it is coming out with all the frequencies precisely mapped. If you choose a generic state, it will decay. And therefore, that's one comment. So therefore, what we do is we just choose on the initial slice, we just choose the Bunch-Davis vacuum. Now, the Bunch-Davis vacuum for massless, massive particles is known to have the full de Sitter symmetry. When the massless particles are present, the de Sitter symmetry is in question. And in any case, our point is that, don't commit yourself to de Sitter. I mean, like in the black hole evaporation, you start off the system with some state. This is the state we use, and this is the result that we find. If then in that, yeah, you can certainly, just like in the case of black hole, there is a time transitional invariant state, which is the Hartle-Hawking state, but that's not the physical question to ask.
Subtlety?
I think gravitons are even more subtle. So this subject is a very murky one. I mean, there are literature is full of conflicting claims, but my understanding of the final word, as I understand for massless particles, is that when you include interactions, it effectively generates a small mass, and then it does admit a de Sitter invariant vacuum. But since graviton is a gauge part, has gauge invariance, it can never acquire a mass. So the question for the de Sitter invariant vacuum is open. But another thing I want to say is that, you know, we are not really in cosmology, you never see the full de Sitter group, because we are really seeing a small patch of the universe. So, you know, how do you know that the scale factor is de Sitter? It could be asymptotically flat, you would never know. So it seems to me to be, it's not a very good question to ask. I mean, commit yourself too much to de Sitter. That's what people have done. They try to analyze quantum effects by committing themselves to de Sitters and then doing perturbations around it, for example. And that's not necessarily the, I believe that this is a better approach. You just compute the quantum effective action and calculate.
I was just asking whether from symmetry considerations also there's an issue.
Could you describe the late universe where you have power law expansion? Is it also true that any two observers will be outside?
Yeah, it's very, you're talking about what is the Penrose diagram?
Yes.
I think power law is really slowing down. I mean, it's almost becoming exponential.
Can you draw it?
Yeah, I have not tried to do, no, I should perhaps try to do that. I have not done it. But I expect that it will have, it's a good question, but since exponentially, yeah, what is the Penrose diagram? I don't know, because eventually it will really become flat. So eventually it should come everything in the horizon. There should be no de Sitter horizon, eventually.
Really? So
I don't know, okay, so what would the Penrose diagram look like? Okay, if I have to hazard a guess, it will look like this.
But aren't you replacing the exponential with a big power? Yeah.
but a power and exponential are qualitatively.
Yeah. No, but eventually, when it becomes flat, it should be Minkowski. So it would be something like a house, the Penrose diagram. But okay, I think it's an interesting question. Yeah, I mean, one can certainly analyze it very cleanly in 2 dimensions, where we have a solution, and it's a question it's a question of causal structures.
So eventually, if it becomes Minkowski, will it be described by a flat space effective field theory?
It will only asymptote to flat space, yeah.
Yes, I mean, but so sufficiently far in the future, will you have a effective field theory without cosmological constant that will describe this? And can you understand this from this quantum theory? I mean, that you had in the, you had a cosmological constant to begin with in the action, right?
Yeah.
So what happened to that?
No, so you should not think about the cosmological constant is not, you have to think in the 4-dimensional space-time, right?
Yes.
It's not the right question to ask on a given slice. What is the cosmological constant? So everything I've done is manifestly coordinate invariant. There is no problem with.
I'm just wondering that, suppose you go to far future, right, where it has become Minkowski.
Okay, suppose we forget about where it comes from.
Yeah.
If I just give you a matter of this particular barotropic index, it's manifestly coordinate invariant, and it just goes to, there is no problem with it.
Yeah, but I'm just wondering that if we had been living in the far future, right, and we see Minkowski space around us, and we might think that it's just Minkowski space, right? The effective field theory that you get will be just field theory without a cosmological constant?
Yes. But then you should do, if you want to study the evolution of the universe, you cannot ask the question at a given slice of time.
Yeah, I'm not studying.
That effective field theory?
Yeah, suppose I'm not interested in the evolution of the universe.
I can completely answer this question in 2 dimensions. In 2 dimensions, you really start with the cosmological constant. But instead of it becoming square root of g, it has a small dependence on 2 log omega a. If you measure the cosmological constant at a later time, starting with a big long scale cosmological constant, it looks as though on that late time slice, it would look as though the vacuum energy is 0. But if you look at the full manifold, it's completely described by a covariant equation. That's the whole point of this, doing the calculation covariant. I mean, that's the whole point of why we went down the Barvinsky-Vilkovisky.
Will Minkowski space be a solution? That's what I'm asking.
No. Minkowski solution will not be a solution. Only in this space, it will, at late times it will look Minkowski, but early times it will not look Minkowski. You have to look at the whole history of the universe. Because you started out with an initial cosmological constant, which was non-zero. There is a term in your effective action, which looks like a Sorry? Because you have to solve not Einstein gravity, but these modified equations. And what you will find is that you will eventually run into a initial singularity where the A is contracted. So this is a solution. So you can, what is there to discuss, right? Yeah, it's not exactly Minkowski, it is approaching.
A similar screening of a cosmological constant has been discussed some time ago by Chamis and Woodard. Is there any connection with this?
No, so that's, so I think they come closest to this. They do look at this, but the way they analyze it is they sit around de Sitter space and do a perturbation. And as you know, even if you have a scalar field, if you expand it around a wrong vacuum and then try to recover the classical equation by doing perturbation theory around the wrong vacuum, you will eventually discover infrared divergences. And that's how they try to arrive at this instability. I find this is a cleaner approach because you just work out the quantum effective action and then try to ask what are the solutions.
It's flat, you get near the 3 brane and you have ADS5 cross S5. ADS5 cross S5 is an exact solution of that theory. In the same way, it would seem that flat space has to be an exact solution of the theory you're describing.
Why?
If it has a limit in the far future where it becomes flat, you must have flat space as an exact solution.
Why? Because the choice of the initial conditions is very important because you're starting the universe off.
Right. But there will be a second solution which is just flat space.
I don't think so. I don't think so because, simply because rho is going to be non-zero. The density, there is a non-trivial density which is a function of time, which is going as rho star a to the minus gamma. And so the energy density is never strictly zero. It goes to zero at infinity, but it's so it's a slowly diluting away, but it never becomes zero. I mean, another way to give you an example, suppose you have just radiation, right? Radiation also, when it completely dilutes away, you will get asymptotically flat space. But that doesn't mean that if you work it backwards, there was no radiation. Yeah. That's because the cosmological constant is a fundamental term in the action. You see, there you had T mu nu, and you created the state of the, here you have to just, so what I'm doing is that I have this action, and I try to find the solutions to this action. That's all I'm doing. But now I'm including quantum corrections. So what I find is that this gets modified in 2 dimensions. Yeah, you will not get a Minkowski space as a solution. No, I mean, if suppose forget about this quantum corrections. If lambda was non-zero, Minkowski space is not a solution. Does that bother you? Why?
Sorry, just one small clarification. I thought you were replacing the exponential of de Sitter space by some large power,
Yeah, here.
But this confuses me because as t, I thought you were taking e to the a of t going like e to the ht, and instead saying it is t to some base power.
It's minus 1 upon gamma. I wrote it wrong. So gamma is going to 0, let's say. So when gamma is going to 0, you write this as e to the gamma h star t to the power minus 1 upon gamma. Oh, sorry, plus 1 upon gamma. Sorry, there is a minus sign wrong here, but I have it. So basically this gamma cancels and you get an exponent. See, you can basically approximate, yeah, you can approximate it a large exponential. No, you can approximate it a large exponential by this, right? That's all I'm using. The limit of this epsilon going to 0 is e to the t. Yeah. Yeah. Exactly. Yeah, it's not flat space. It's asymptotically flat space. It's not flat space, it's sort of asymptoting to the curvature is becoming 0. Yeah, but it's still accelerating very slowly.